Hey, welcome guys. Yeah, you see some video. Yeah. Okay, so yeah, so in this video, let's prove this so-called small finite group structure. So basically in this video, I will prove that these are all the small groups from order 1 to 15, and I will prove all of it except for 12. 12 is a little bit difficult, so I postpone to next video. And basically, the tool is just what I said. Yeah, basically, just to see those theorem, a theorem video. So if you have not yet seen my theorem video, I suggest that you go to see it. Okay, so let's start. Oh, subscribe to my channel. Okay, so this is our goal. So our goal is to prove this table, except for 12. Okay, so this is I copy from the grid. So abstract algebra. Yeah, so let me just quick out. So Cn is basically the chemistry notation. So basically Zn, so cyclic group with order n. Okay, so remember that let me just quickly tell that the basic theorem that we already proved in the previous group theory video. So the first, if G is P, if the order is a prime, which is a cyclic. Okay, so remember this is proved by Lagrange's theorem. The second is that when G is prime square, the order is prime square. So this is also cyclic. Sorry, this is abelian. This is by a so-called class equation. Okay. And so the first two, without zero theorem, you can easily prove it. Okay. Okay, so the number 3 and number 4 is basically what I got to prove. Is that when G is 2p, where P is prime, and G is cyclic or dihedral. Okay, so this is so-called dp. This is so-called Z2p. Okay, and the number 4, which if G is has 2 prime number, P times Q, and P larger than Q, and Q do not divide P minus 1, then it will be cyclic. Okay. 3 and 4 are using the zero theorem. Okay, and we will, and the number 5 is classify the group with order 8. Okay, so let's see what we gonna to feel happy about the results. Okay, so let's see. So G is prime, we can kill some stupid guy, right? So we get a muscle 2 must be, maybe I change the color. So 2 must be let's say, I guess maybe blue is okay. So 2 is also a cyclic. Okay, so 3 is prime, cyclic, 5 is prime, 7 is prime, 11 is prime, 13 is prime. Okay, so we are happy. And also we know that prime power is abelian, right? So if this is, so for example, if G is order 4, then it basically is C2 times C2 or C4. Okay, so this is famous so-called Klein group. G is 9. Then by the classification of abelian group, we get a C3 times C3, or basically Z3 times Z3, or basically Z9. So we have 2 different group. So let's go back to this list and wipe out these 2. Okay, so the remaining 6, 8, 10, 15, and 14, and 12. Okay, so the 12 I will postpone to the next video. There are 5 different groups. There are 5 different groups in the 12. Yeah, 5 different groups, and the 5 different groups for 8, and the 10, and yeah. So let's prove 2p. Okay, so let's prove 3. Okay, so once you prove 3, that if you choose p to 3, then the group 6 will be cyclic or dihedral. Okay, so this guy actually is a cyclic. This guy is a dihedral. And you will also solve the 10, right? Because 10 is 2 times 5. And I think, yeah, so basically you will solve 9 and 6 and 10. Okay. Okay, so without wasting you guys' time, so let's go to the theorem. G is 2p, where p is prime. And G must be a cyclic or dihedral. Okay, so let me just write the dihedral P definition. So dP is basically dihedral group, and generated by us RS, generated by the RS, such that the R squared, RP minus, RP, and the S squared is 1, and the SRS inverse is R inverse, I think. Okay. Yeah, sorry. Yeah. So the mathematical idea is that you get some regular polygon with the P sides, and then the R is a rotation, right? So R goes to P is 1, and S is a reflection, and S squared is 1. So, and then you can easily show this. Okay. Okay, so the tool is Zito theorem. Okay, so I think this one maybe we don't need a lot of Zito theorem, right? So now let's only focus on when P greater than or equal to 3, because when P equals to 2, we already proved it. So when P greater or equal to 3, let's see, right? So by the Zito theorem, so using the Zito. So in this video, we should only use the Zito first theorem. So I proved 10 of them shit, but I only used one of it. So using the Zito theorem, we know that there's only one. There's only one Zito P. Okay. Let P. Okay. Because we know that NP is 1 mod P, right? And NP divide 2. So NP is only 1. Okay, so this guy will be normal, right? So that means your group G have some Zito P group ZP, right? So let's say the generator is R. Okay, so this G, right? This G could be one set of the element will be 1 R squared up to RP minus 1. Okay, this is come from ZP. And I know that the G has 2P, right? So I can take another element called S, right? So notice that from here, we also know that there's a Zito, there must be Zito 2 group, right? So, and S is not inside the P and 2 and prime, right? So this S must be the Zito 2 group. So S must inside the Zito 2 group. Okay. So, or basically you can say that the G, you can easily say that, or okay, if you do not believe, then it's fine, right? You just take some S and you multiply by this. So RS SR squared SR P minus 1. Okay. So total you have 2P element, and easy to show that these two, all of these are different, and they cannot be the same. Right. So these are all the elements you can have. Okay. Okay. So yeah, one. So you can easily you can ask. Yeah, you can see that. Okay. So you can see your G, right? So yeah. So since there is a Zito 2 group, right? So I can define this S to be some generator of some Zito 2 group. Okay. So I can just let S to be the generator of the Zito 2 group. By definition, by a Zito theorem, there's always Zito 2 group. Okay, so S squared will be 1, and I can make this table, right? So the only problem is that we need to figure out what is RS R inverse. Okay, so it's SRS inverse. Why? Because ZP is normal. Okay, so that means let's say this is maybe A. Okay, so that means AG must be equal to AG for all G belongs to G. Right, so if I take G to be S, then I take A to one element called R, right? So I get R, SR must be R to some power S minus. So the key is that we just need to find this power, okay? So we only need to, so now we already get our group. Must be generated by RS, such that the RP and S squared is 1, and the SRS equals to R to something. Let's say this guy is K, okay? So we just need to determine this K. And yeah, I think this is simple. So let's see. So R is S squared A So right, s squared r and the s minus 2, right? So this is so s minus 1 is just s. Okay. So I can write as SR as inverse S inverse. So this is SRK as inverse. Okay. And also this guy can be written as SR as inverse to the power K. And this guy is also RK, right? So it's RK squared, right? So from here, you know that R and RK squared, right? So K squared minus 1 must be mod P, 0 mod P, right? But the problem is that P is prime, right? So there's only two cases where P divides K minus 1 or P divides K plus 1. Okay, so let's see. So if P divides K minus 1 means that what? Means that means like this K is just P plus 1, right? So that means SR is RS. So this guy will give me abelian group. Okay, so let me just write down. So if P equal divides K minus 1 means that the RS as R SRS inverse is just R, right? So which give you, so R is just a commute, right? So it gives you the abelian group, which is just ZP cross Z2. Okay, by this, right? Because they commute, their generator commute, so they commute. Okay, and if P equals to K plus 1, right? I can just write P equals to K plus 1 without loss of generosity. So get SRS inverse is basically R P minus 1. So it's R inverse, right? By definition, this is a dihedral group. Okay. Yeah, right. So if this is minus 1, then we get our definition of the dihedral group. It's exactly the same. Okay. So now let's go back to our table. Yeah, so we finish this and finish this. Okay, so how about also it's 14? Okay, how about this 15? 15 just very easy. So let's walk and see. So G is PQ, P that greater than Q, and then Q that divides P minus 1, give you a cyclic. Okay, so let me just, so one can easily see that now the NP just 1, right? Because P greater than Q. Right, so NP must be 1 mod P, right? But P greater than, and NP divides Q, but P greater than Q minus Q, right? So NP can only choose 1, right? So NP is 1. And then from here, you know that NQ is 1. Okay, so which tell you that in this case, you have a pseudo P group, pseudo Q group, and they are all 1, and both of them are normal, right? So and the P intersection Q, your pseudo group ZP intersection ZQ must be identity, right? So this G must be the product of these two cyclic groups. Okay, so they are cyclic. Yeah, so this one is also very trivial because in this case, the pseudo P group and pseudo Q group are only 1, so they are normal sort of product. Okay. Okay, so the remaining is the little bit difficult. So let's just go to see the results. Okay, so theorem where G equals to 8 must be the following. Okay, so first case that the G is abelian. Okay, so if G is abelian, then by the classification, abelian group must just direct some cyclic. Right, so it's Z2 twice Z2, and I guess that's Z8. Okay, so this is just sorry, this is sorry, I'm stupid. This is Z4, there is some Z2, Z8, and 3 Z2, Z2, Z2. Okay, and the following two different abelian group. I think one people, I guess you guys already know is dihedral group D4, generated by, let's say, I use AB now. I guess it's the A squared, A4B squared. It's 1, and BAB is just A inverse. Okay. And also a so-called Q, which is a quaternion. Okay. Quaternion is basically generated by AB. A4 is 1. And I think B squared. Okay, so B squared now is just A squared. And also BAB is A inverse. Okay, so let me just say about the quaternion. So quaternion is generated has 5 8th element. So it's plus or minus 1, plus or minus I, plus or minus j, plus or minus k. And the relation is basically multiplication. So ij is k, jk is I, ki is j, and ji is minus k, kj is minus I, and ik is minus j. Okay, so you can check this is a group. And so the problem is that how do we see Q is not isomorphic to D4? Okay, so I think the only you need to check that the order of the group. Yeah, so let me just quickly check for you. So yeah, so what is the, so let's see, right? The Q has 1 minus 1, I minus I, j minus j, k minus k. So what is the order of the 1, right? Also 1, so minus 1 squared is 1, so I squared is minus 1. Sorry, I didn't write, so I squared minus 1, j squared minus 1, k squared minus 1. Okay, so I squared is minus 1, so the order is 4, 4, 4, 4, order 4, 4. Okay, so this is order 2, right? So you get this is 2. But in the D4, you get you have this a to the 4 is 1, right? So in this here, that a square square is 1, and b square is 1. So a square and b are both order 2, but in this quaternion, you only have one element which is order 2, so they are not isomorphic. Okay, so this theorem says that if G is 8, then it must be only 5 of them. Okay, so this is the tricky part. Okay. Proof. Okay, so I think G is not abelian. If G is abelian, then I don't care, right? I only care when G is not abelian. Okay. So my claim is that my first claim is that if G is 8, so now G is 8 and non-abelian. And I want to mathematical proof that it must be D4 and Q, right? So if G is 8, let's see, right? If G is 8, then and what? Okay, so G must have some element has order some I should say some subgroup has order 4. Okay, so that means G must have something that's called A, which is subgroup of G, such that A to the 4 is 1. Okay, why this is true? Because this guy is non-abelian, right? So the order of the any element A can only be 1 or 2 or 4. If it's 1, which is not, if it's 1, it's impossible, right? So there A must be 1, 2, 4, 8. And if it's 8, then this group will be cyclic. So it cannot be 8. And you can easily show that if a group, then if there is a group which every group element has order 2, then this guy must be abelian. Okay, so the reason is that if any, so let's say if you have any element xy, which they are both of the element order 2 except for identity, then we get this. Right, but remember that the y squared is 1, so y is y inverse, and x is x inverse, right? So you get yx. Okay, so 2 is not impossible, right? So the only case is 4. So there always has A, which its order is 4. Okay, so let's call this sub generator is A. Okay. Okay, so now here comes the problem. Okay, so it's very simple, right? So let we start. So our group G must be written as a 1A squared A cube. Okay. And what? And let's say A is generated by A, right? So A is subgroup of G, which index is 2, right? So index to group must be normal. Okay, so right, so we let's say I take some element called B, which is the G outside A, right? So I take some element which is B, Right, so I can easily just do the same thing. I can say that, oh, this is BA square, BA cube, and then they are all different. And they are normal, right? So BA must be AB. Okay. Okay. So yeah, right. Okay. So that means what? That means AB, right? AB has order two, in G quotient A. Okay. And then you can ask. So let's say, ask. So that means what is B squared? Okay, so what we can add, I can ask what is B squared, right? So by this I know that B squared must belongs to A. This is obviously correct, right? So B squared must belongs to A due to this, and the ABS index order 2. So B squared must be A. So let's ask what is the possible case. Okay, so what's the possible case of B squared belongs to A? Okay, so there are 4 cases, right? So B squared can be 1, B squared can be A, B squared A squared. Okay, so this is very stupid, right? So if B squared is 1, which makes sense, right? Can have B squared equals to A cannot happen, right? Otherwise, that if B squared is A, that means what? That means this group G has order 8, right? So it will make it become cyclic, right? Because A is B squared, so AQ will be B4. So so A is generated by B, and every group is so this group is generated by B, which is cyclic, which is non-abelian. Okay. And possible, this is possible. Okay. So what is this? So this is the same, right? B squared is A minus 1, then it will become this because the whole group will be generated by B. Okay, so these guys. Now, okay, so we got 2 important possibilities, which is exactly these 2 possibilities. Okay, so the final thing, just need to check these 2. Okay. So the same reason. So we know that AB is BA, right? So I take element A. So I get B inverse must belongs to A. Okay, so we need to ask what is the possibilities, right? So 4 possibilities, BAB inverse is 1, BAB inverse is A, BAB inverse is A squared, BAB inverse is A cube. Okay. So let's do some stupid game, do some elimination. This is not impossible, right? Otherwise, that BA is the B, then A is identity, which do not make sense. This guy will make the abelian group go home. So there are 2 cases, right? By the way, so this BAB inverse is just A inverse, right? So this is what we got, what we have. Okay, so is it possible this guy? So is it possible to have? Is it possible to have BAB inverse is A squared? BAB inverse is A squared. Okay, so let's see. Okay. Okay, so if I square this, now I get what? BA squared B inverse is A to the 4, right? So it's identity. So B squared, BA squared will be B, right? So A squared will be 1, right? Which do not make sense because I say that the A has order 2, 4, right? So these do not make sense. So the only case is that BAB inverse is A minus 1, and then we get all these 2 possible cases. Okay, so we just proved that it must be D4 in the cube. Okay, so this is a whole proof. So I will post the timestamp below so you can check wherever you want. So yeah, so we prove 8. Okay, so next video, let's go to some other the most difficult part in this table, which is a 12. So I need to introduce where T, and then it's A4, right? So this A4 is basically the the alternating group of the order 4, and dihedral group. Also, there are some strange guy called T. Okay, so this T, interesting. We will figure it out. See you guys next videos.